this problem, I'm like, well, now let's go ahead and draw a box. And I'll draw my variables under my box. There's my gas in my box. Okay. And then we have what is the pressure of the gas in there, what is the volume that's containing the gas, what's the number of moles of gas particles, and what's the temperature that that gas is running around at. So let's just start plugging. So we have 25 degrees Celsius. And you know that we're going to have to add 273 and fix that. So actually, my fixing the semester, if I draw a circle around that, means we need to fix it. We have a pressure of 1.22 atmospheres, which with the ideal gas law, ideal gas law constant that we're using, that would be the right number, the right units. Okay, but there is no volume or number of moles. So actually, the way this works is we are supposed to express that gas in terms of grams of argon per liter per liter. So do you guys buy this, that grams is not moles, but grams is an amount? If we can go ahead and get N over V, okay, does that not kind of look like G over L? We're just a molar mass away, and that's exactly how we're going to work this problem. Okay, so on the next slide, you know, we're going to rearrange PV equals nRT to get, what I say, N over V. Okay, again, it's the algebra that gets all of us, okay, myself included. But so I guess I would divide both sides by N and then multiply both sides, or divide both sides by NP maybe. Okay, but anyway, if you do it correctly, N over V is equal to the pressure divided by the ideal gas law constant times the temperature in the bottom. Okay, so that's how we're going to skin this cat. There's probably more than one way to skin this cat, unfortunately. So once we have it in units of moles per liter, we know that we can get to grams per liter using the molar mass of this gas, argon. So here we go. Pressure's fine, 1.22 atmospheres. The temperature needs some fixing. We need to add 273.15 units to it. Notice that don't get sloppy with your rounding. There's, since we're adding to fix our temperature, we round according to decimals. We have no decimals in 25 degrees Celsius. We have 2 decimals in 273.15. So we are allowed no decimals. Okay, so let's plug and chug. Now, on your test on next Friday, your final exam, the last section has problems, and you have to, when you do problems, you have to do all the things we know about problems, which includes including units. Okay, so we know we need to put pressure in the top, R in the bottom, and also temperature in the bottom. But the beauty of including units, I would argue, is we should be able to cancel units. So let's see. This atmosphere actually cancels with this atmosphere because they're both what we say in the numerator of their various numerator of the numerator, numerator of denominator. And I bet you buy this that this Kelvin and this Kelvin cancel. So what we end up with is the only units we have are liters per mole in the denominator. And I think I mumbled something like this before, that if you have a ratio in the denominator and you want to go ahead and resolve it and make it normal, basically you bring it up and flip it. So this actually is the same thing as units of moles per liter, which is exactly what we're after. No, well, it's on our way to what we're after, grams per liter. So rounding it according to 3 significant figures, you should get 0.0499. And units would be moles per liter, but we're not done. Now, some gas law problems, it's funny how you work these things for years and you're like, oh, well, that's interesting. So some gas law problems, they will give you the gas, the name of the gas, and they did for this one, and we need actually the name of the gas because we can look at the periodic table and look up the molar mass for argon is 39.95 grams per mole. So now if we take that 0.499 moles per liter times 39.95 grams per mole, which is the molar mass for argon, now units of moles will cancel. And we'll be left with units of grams per liter, which is exactly what we wanted. So rounding to 3 significant figures, it's 1.99 grams per liter. And that's it. It's what's called a density problem. Okay, so we have just a couple other topics in this part. I almost brought my beach ball. There's like a beach ball in the chem lab. You're like, why in the heck did she have a beach ball? It's got the colors, the orange, the yellow, the white, you know. And actually, that is to contain the volume of that beach ball is supposed to be 22.414 liters. So here's how it works with gases. With gases, there are standard conditions for temperature and standard conditions for pressure, just like there are for thermodynamic problems, but they're slightly different. For thermodynamic problems, we said it was 25 degrees Celsius, 1 bar, okay? For gas law problems, it's 0 degrees Celsius, okay, and 1 atmosphere, which the pressure is similar, but the temperature is not. So that's what we call standard temperature and pressure for gases. Well, here's the deal. If you go ahead and say, I'm going to have 1 mole of any gas, I'm going to have 1 mole of any gas, argon, carbon dioxide, water vapor. If you plug into, this used to boggle my brain, but I don't really think it's any big deal. PV is equal to nRT. If you plug a pressure of 1 atmosphere, leave the volume alone, moles of 1.00 moles, however many sig figs you want. Of course, R is R. And if you put the standard temperature, which is 0 degrees Celsius, 273.15 Kelvin, okay, you automatically then can solve for your V. Okay, so that ball is actually 20, I don't remember that, I said 22.414 liters. Okay, so I don't know. Kind of some people memorize that. Okay, so the last problem I want to talk about doesn't involve the ideal gas law constant. It's called the combined gas law. But we start out with the ideal gas law, PV equals nRT. And if we're going to talk about state 1 and state 2, where the number of moles stay the same, we're going to put N, the number of moles, next to R, because it's going to stay constant. Okay. So if N is constant, we're not changing the number of moles, then for a given gas, as long as N stays the same, if you multiply the pressure and the volume and divide by the temperature, which can vary, they should always equal some constant, as long as N is the same. So that kind of gives us kind of this neat sort of situation. We can play around with gases at 2 different states. So you see little subscript 1s? That's state 1. Okay? Little subscripts 2s? That's state 2. Okay? So we have P1 V1 over T1 is equal to P2 V2 over T2. State 1 and state 2. As long as N is constant. Okay? It's helpful. So let's work a problem. And I'm not going to, you know what I've been doing is like drawing a picture of a box sometimes and then pulling out P, V, N, and T for everything. Actually, what I want to do is on the next slide. So what I would usually do is kind of start 2 columns. I have the state 1 and state 2. Okay? So we have a whole lot of words here, but you're going to see those words unpacked here on the next page. So if you look at that paragraph, you should be able to pick out what's the conditions for the first state. Okay, this gas is going to start at a pressure of 322 millimeters of mercury. It's going to start at a volume of 33.5 milliliters, and it's going to start at a temperature of 12 degrees Celsius. Now, that combined gas law, okay, it looks really busy. I count 6 variables. Do you count 6 variables? So the way this works is, this sort of problem is you know 5 of them, but you only have 1 you don't know. And if you look at the paragraph, unpacking those words, the second state is going to be the new pressure is 353 millimeters of mercury. The new volume is 46.7 milliliters, and we're in this case supposed to solve for the temperature, but it could have been any of those variables. Okay. Now this is where, like I said, my algebra skills, sometimes I have to concentrate a lot. Now, do you see where we don't have the ideal gas law constant in here? There's no R value. There's no R value in this. The beauty of that actually means that with regard to pressure, you can leave pressure in the same units as long as it's the same in state 1 and state 2. We can leave pressure in millimeters of mercury. Since we're not using the ideal gas law constant, we don't have to convert to atmospheres. Yay! We can leave volume in milliliters, because here in a minute you're going to see actually those things are going to cancel each other out when we start plugging in. Temperature, you have to convert to Kelvin. You have to convert to Kelvin or you will not get the right answer. Okay, so let's go ahead and see what this looks like. So basically, we're going to rearrange the combined gas law and solve for T2. So let's go ahead and fix our temperature 1. 12 degrees Celsius really is 285 Kelvin. Okay, and of course, we're trying to find the other temperature. So if you're like, I don't know if you're like me, but the way I learned this, the way I probably do it, because if I don't want to mess it up, is I learned kind of, it's called, I think of it as kind of like a flattening out, kind of like a cross multiply. I can rewrite this as P1V1 T2 is equal to, I'm just flattening out, you don't have to do this, is equal to P2V2 T1. See how I kind of crisscross just to make it flatter. And to me, that helps because I'm less likely to screw up. So I want to get T2 by itself, so I can rewrite this and say T2 is equal to, and usually we combine the, if we can, we combine the P's and the V's. So for instance, T2 is equal to P2 over P1. You buy that? Because I'm going to divide by P1 times V2 over V1. We good with that? And then I have to take T1 along for the ride. Does that look okay? All right. So honestly, this is why we can leave units of pressure in millimeters of mercury, and we can leave units of liters in milliliters, because they're going to cancel each other out. So when we substitute in, this is what we're going to substitute in for. To get the Kelvin temperature, we're going to take the P2 divided by P1 times V2 divided by V1 times T1. I've seen students like just plug into the top equation first, but I really like rearranging it first. So here we go. So your pressures, your P2 is 353 millimeters of mercury divided by P1, which is 322 millimeters of mercury. Then we go to the volume term. Your V2 was 46.7 milliliters divided by V1, which is 33.5 milliliters. And then we tack on the Kelvin temperature for T1, which is 285 Kelvin. Now, of course, units are looking pretty clear. Units of pressure cancel, units of volume cancel, and we're left with units of Kelvin. And it looks like we're allowed 3 significant figures. So the T2 Kelvin temperature is 436 Kelvin. Not bad. Can't remember if I asked to get in Celsius. Oh, looks like we're going to go ahead and put it in Celsius. Okay. So remember, you're going to want to be fluent in going back and forth between Kelvin and Celsius. So to get back to Celsius, then we subtract 273. 273, 273.15. It's the same diff in this case because we're only going to have to round to 0 decimals anyway. But you could have put minus 273.15. You got the same answer. So that's it. Okay. So if the moles, N is held constant, and the temperature is held constant, we get all excited because actually things simplify and we can come up with P1V1 is equal to P2V2. Okay. If the moles and the volume's held constant, we get this relationship. Okay. And if the pressure and the moles are held constant, we get this relationship. But I wouldn't memorize all those. I don't see why you'd want to, but it's just me. Okay, so we'll take a quick look at these. They do kind of come in pairs, right? We have the 23, 24, 35, 36, and 41, 42. So do you guys have those hints about, you know, I think you'll be fine. So this is what those look like. They look like this. So 23 looks like something we just did. When you unpack everything, all you're missing is V2. You should be fine. Don't forget to fix your temperatures though. Let's see, the next one. This is the next one. It's a little different. So notice I actually added in N, N1 and N2. In this case, your volume is held constant. And actually, you're jacking up the moles of gas from 10 to 12.5 because you're adding 2.5 grams of gas, if you read the problem a few times. So down here, I told you what I would do. There's different ways to skin this cat, okay? But if my volume is held constant, that's why over here I went ahead and combined the volume and the ideal gas law constant, and then I just had pressure, number of moles, which is changing because we're adding more gas divided by temperature. And then actually we kind of come up with a different form of the equation we've been using. So that's the way I do it. This is a density problem. Okay, no, it's a molar mass problem. Okay, so you're given everything but the number of moles for the gas. Okay, you can get the number of moles for the gas using the ideal gas law equation, PV equals nRT. Once you have moles, actually, if you divide moles by the mass that they give you of the gas, moles per gram, actually that's the molar mass. That's what you're after. Okay, now we have a few problems where earlier on in the course, which you're going to see on your comprehensive final exam, there were times when you wanted to find the concentration of a solution in different units. And I said, go ahead and choose a basis that works for you. That's what these problems remind me of. If you read the information a little bit, notice they give you the density of grams of gas per liter that gas would be bouncing around in at a given temperature and pressure. So if we choose as 1 liter as our basis, things kind of fall into place. If 1 liter of gas is our basis at that temperature and pressure, then of course the mass is 0.841 grams. Pressure was given, the volume by definition, so we've set it as 1.0 liters, the pressure was given. We can solve for N. Okay, now we've got everything we can solve for N. Okay. And then once you have N, okay, if you take, to get the molar mass of this thing, it's just grams per mole, mass per N. Okay. So it's the same as, it ends the same as the other one. And is this almost the last one? All right, again, I would choose a 1 liter basis because notice they give the density is 1.80 grams per 1 liter. Well, dang, let's just choose 1 liter. We'll go with the 32 degrees Celsius. Okay, notice in this case they give you the identity of the gas, kind of like the argon problem. You do need to know it's nitrogen this time. Okay, so the reason you need to know it's nitrogen is we can go ahead and knock out N this time because we have the mass, and for N2 we can calculate the molar mass. So you can use grams, the molar mass of N2 to come up with the moles. That's actually your first step here. Then the only thing you're missing is pressure. So you can use the ideal gas law equation to knock out pressure. There is another one. Oh my gosh. Okay, similar, I think. Okay, I think you'll do fine. So let's go ahead and see what we can do with part 2. All right. So combining stoichiometry with gas law problems, basically. So we'll jump right in there, all right? Let's do like what we used to do with stoichiometric calculations, basically kind of take from the paragraph and unpack it underneath the species it's talking about. So it says, what volume of H2 gas? So here we go. Where's my H2 gas? There it is. Actually, under here, I'm going to go ahead and write my variables. P is equal to V is equal to N is equal to T is equal to. How's that? Okay. So what volume of H2, so volume is equal to question mark. Okay. And notice for H2, it gives me the temperature and the pressure. I'll go ahead and put that in there. Temperature is 22, which I'm going to have to fix, 22 degrees Celsius. Pressure is 1.00 atmospheres. All right. What volume can be produced? And it goes on to say you have 2.50 grams of zinc. So find the zinc, and we've got 2.5 grams of zinc. 50 grams of zinc. And it says we have excess HCl. So cool. Does this make sense that I can take the mass of zinc and I can do the stoichiometric magic to get to moles of H2? Okay, that's exactly what I'm going to do. I'm going to go from mass of zinc to moles of zinc, and then moles of zinc to moles of H2, basically. Once you have moles of H2, dang, you have that. And at that point, you basically can use PV equals nRT because you only have one unknown. That's the way you skin this cat. That's what I would do. So here's the calculation that we learned earlier. How do you get from grams of zinc to moles of H2? So we're going to use the molar mass of zinc. So we're going to take 2.50 grams of zinc over 1 times the molar mass of zinc, the flipped version, 1 mole of zinc over 65.39 grams of zinc. That's from the periodic table. And so the moles of zinc are 0.0382 moles of zinc. Now we're going to use the stoichiometry. It seems like just the other day we were talking about this. So we have 1-to-1 relationship. So I would put that number over 1.08, so 0.0382 moles of zinc over 1 times 1 mole of H2 over 1 mole of zinc. So remember where that this is your stoichiometric ratio that came from these ones down here. And yes, you need to show that step. So that's our N ready to plug into PV equals nRT to get the whatever we're after for H2. I even forgot. Must be after volume. So if we rearrange PV equals nRT, solving for volume, volume is equal to nRT over P. So here we go. Oh, let's fix our T. So our temperature in Celsius was 22 Celsius plus 273 units. That gives us 295 Kelvin. So now let's plug it in. So the volume is equal to the moles, which is 0.0382 moles, times R, which is 0.082058. Units of R is liters atmospheres per mole Kelvin, times temperature in the numerator, 295 Kelvin. All of that's divided by pressure, which is 1.00 atmospheres. It looks like we've got 3 significant figures going. So our answer is 0.925 liters. Now, to know that it's liters, you can either just look at the volume and know it's got to be liters, or, even more fun, you can go back and see what canceled. So moles have canceled, units of Kelvin have canceled, units of atmospheres have canceled, and we're left with units of liters. That's it. Combining gas laws and stoichiometry. Let's do another one. Let's kind of, again, pull out what we've got and put it under where it goes. Okay, so to me, that's easy, less likely to make a mistake. So with regard to the hydrogen, I'll go ahead and P is equal to V is equal to N is equal to T is equal to. With regard to the hydrogen, the volume is 125 liters. Oh goodness, they give us temperature in Kelvin. Go figure. 298 Kelvin. And a pressure of 0.783 atmospheres are combined with excess. We know that's important, so then any sort of yield that we get is based upon the limited reactant, which is H2. Okay. Oh, here's the question down here. So how many liters of NH3 will be produced? So we have a P is equal to V, N is equal to T is equal to. So question mark liters. I don't know. Notice they go ahead, they say that your product, your NH3, is going to be at standard temperature and pressure. So standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. Cool. All right. So it's kind of like when we did titrations, where you start with whatever you know the most about. Okay, we definitely know the most about the H2. We can knock out N using PV equals nRT. Okay, so that's kind of what we're going to do. Knock out N, and then use stoichiometry to get to this N, plug it in, and then use PV equals nRT to get to that volume. So here we go. So we need to get to the number of moles of hydrogen. So if we rearrange PV equals nRT solving for N, N is equal to PV over RT. Do we have some fixing to do? Maybe not. Okay. So for the hydrogen, we have the temperature in Kelvin, we have the pressure in atmospheres, and we have the volume in liters. We are good to go. Okay. So the number of moles of hydrogen is 0.783 atmospheres times 125 liters divided by the ideal gas law constant, 0.082058. Units for this constant we're using are liters, atmospheres per mole Kelvin. Also in the denominator is the temperature, 298 Kelvin. So let's cancel units. Looks like units of atmosphere cancel, units of liters cancel, units of Kelvin cancel, and we're left with basically 1 over moles in the denominator, which if you flip it and bring it up, you get moles, which is exactly what we want. So rounded according to 3 significant figures, the answer is 4.00 moles of hydrogen. Now, if you're like me, you're like, that sounds too, like, just symmetrical. Sounds wrong. But apparently it's not. 4.00 moles of hydrogen. Now we can use that moles in stoichiometry to get to the moles of the product. So the next step, we're going to start, our first term is going to be 4.00 moles of H2, probably over 1 if I was doing it. And then our ratio from the stoichiometry of our equation, 2 moles of NH3 in the top divided by 3 moles of H2 in the bottom. Moles of H2 cancel, we're left with moles of NH3. And we need to round according to significant figures. There's no uncertainty in the 2 or the 3, but there is uncertainty in the 4.00. So 3 sig figs, 2.67 moles NH3. Now we're going to use PV equals nRT again In this case, we're going to solve for the volume of the NH3. So volume is equal to nRT over P. That's like almost poetic. Okay. Oh, that's right. I was like, what? So in the previous part with the beach ball in the chem lab that has a volume of 22.414 liters supposedly, okay? If the gas is at standard temperature and pressure, that is 1 mole. Okay? So actually we can use that as an equality that works for this sort of thing, since the ammonia is at standard temperature and pressure. So I think this is, do I have it on my notes? Yeah. If we want to use that kind of quick and dirty, this is an alternative to using P equals nRT one more time. We could use P equals nRT solving for V. Or we could just recognize that since it's at standard temperature and pressure, 1 mole is equal to 22.414 liters. And then moles of ammonia cancel, and then we're left with liters of NH3. We need to round according to 3 significant figures. So whether you use P equals nRT solving for V, or in this case, you'd still get 59.8 liters of ammonia. To be honest, if I was on a roll working problems, this probably would not come to mind. But it is good, very valid. All right, yet another one. Let's see what we got. This is still the same reaction. What's so good about this reaction is that notice that they are all 3 in their gas phase. All right, so under hydrogen, we have some things that are known. They say the volume is 25.0 liters. The temperature is 25 also, but 0.0 degrees Celsius. The pressure is 1.25 atmospheres. They combine it again with excess nitrogen. Okay, now isn't this what we just did? I guess it feels different. But I guess if we go over here to the ammonia, you're supposed to come up with, again, the volume of ammonia, but it's not at standard temperature and pressure. But it is at something kind of handy-dandy. So with regard to the ammonia, notice the ammonia is at 25 degrees Celsius. And it's also at 1.25 atmospheres. Again, I may not, if I was working this problem, I may not catch that, but that does throw you into something kind of cool. Okay? If you have 2 gases and they aren't the same temperature and pressure like this, then guess what? According to Avogadro's law, their volume and moles are directly proportional. Okay, so that actually is kind of a nice little thing. Let's see. Yeah. So in either case, whether you use kind of the quick trip I'm going to show you with Avogadro's law or not, you have to come up with what is the number of moles here. So to come up with the number of moles, we can rearrange. I think you still have to come up with the number of moles. I guess you don't. Wow, okay. So at the same temperature and pressure, we're ready to just make use of the fact that the volume and moles are proportional. From the stoichiometry of the equation, we know that 2 moles of NH3 are formed for every 3 moles of H2 reacted. That means that you should have 2 liters of NH3 formed for every 3 liters of H2 that are reacted. Yeah. And since we already have the volume of H2, we're just ready to plug. It did make our life a lot easier. So let's knock this out. Let's start with the given volume of H2, the limited reactants, 25.0 liters of H2, and then plug in that ratio. 2 liters of NH3 for every 3 liters of H2 that came right from the balanced equation. So liters of H2 cancel, we're left with liters of NH3, still round to 3 significant figures. You get 16.7 liters of NH3. That's pretty cool. And you're done. But you could have done it the other way too. That's a lot easier. But that's only a special case. Okay, so this just happened to be, and I guess if you kind of lay it out like I've been doing this afternoon, those might be more hitting you in the face if you have the same, in this case, temperature and pressure. So, yay for Avogadro. All right. Assignment slide. Well, if it's any consolation, we aren't going on to part 3 today. And these are only 3 problems, so let's take a look at them.
And then these 2 assignment slides will be due Monday.
Yeah, these will also be due. Yep. Okay, so the first one looks like this. Where, do you remember, wasn't it in Gen Chem 1 where you guys had like a mixture of potassium-containing compounds and you had to, oh, maybe that's something else. Well, anyway, we've got potassium chloride and potassium chlorate. And we're going to heat it up and it's going to decompose. Now the mixture, the cool thing about this is actually the KCl, when you heat it up, does not decompose, but the KClO3 creates oxygen. So the way this works and the reason why it's in, you can go if you want, or I'll just keep talking. I'm sorry, but I just wanted to assure you it'd be fine with me, because we're really done with lecture now. I'm just kind of talking to myself. So the cool thing is it's the oxygen that you look at. Notice we're given the pressure, the volume, and the temperature of the oxygen. You can get moles from that, and then actually you can backtrack then and get, from stoichiometry, moles of KClO3. Then you can convert that to grams, and then actually you can compare that mass to the mass of the mixture, which is 3.57 grams. So then the other one looks like this. I kind of have it up there for you. I'll post these in case you're. And the next one looks like this. Okay? So, voila, QED. Have a good weekend.
All right.